Hi, welcome back to CET3116. In our last video, we start analyzing the flip-flop rising edge trigger in this case. And if you remember, we used to the gated latches. This, remember, is the truth table for the gated latch. And now we use a clock for our first time in the analysis, and this clock, well, is connected in a very peculiar way. So the first D latch, if you remember, was connected with a clock, or the gate was clocked with an inverter, whereas the next, the output latch was connected without inverting the clock. So the effect of that, if you remember, is that we have these two latches, one working in whole, while the other one is actively changing the output or following the input of the latch. If you remember, this is exactly what we have in the truth table. If gate input is 0, that will correspond to the clock down, then there's no changes that will occur. So you may change everything in the input of the gate, and then it will just stay. The output will be maintained. Okay, in this case 0, 1, 0, 1, while G is 0. On the contrary, when we have G equals to 1, then every change in D will be transferred into the output. So we have these two gates in which one is behaving in a whole, and while the other one is doing the following the input. And when the clock change, it simply reverses, or combines the opposite, right? So if you remember, then our changes will occur in this case when the clock goes from 0 to 1, right? That's why we call this rising edge of the clock. So in this case, our input was stable. At this point, the clock goes from 0 to 1, and then the P gets stable, and the output will basically follow in the output of the flip-flop will follow the value of P, and then this is exactly when the value of P was latch, right? Until when? Well, it will do the same thing in the next cycle, and whenever the clock goes from 0 to 1, the next change, in this case, you'll see that we're picking the value of D that goes is 0, and therefore that's the value of P, and then the value of P will be transmitted at this point to the output. Okay, so remember, we have these two state of the clock, or semi-cycles of the clock, for which we have G1 is high, and then whatever changes in the input, P will follow, and this is exactly what's going on. The next case is when the other gate, in which we have the clock reversed, and then G2 is then high, therefore Q, this output, will follow whatever P is. But P is supposed to be stable, and this is what keep P at the point in which the clock goes again to from, in this case, go from high to low. The input and P changes. However, the Q, or the output, will stay until the next rising edge of the clock. So this clock as a whole changes only during the rising edge of the clock. Very, very important, this concept, because you can imagine, well, what is the reason that we do that? Well, first of all, we keep everything restricted for changes up to that precise instance in which the clock goes from 0 to 1. Okay, so we could use that, great benefit because that provides a lot of stability. So you want to see, as I mentioned, as we go through the sequential circuit, that this is a very important feature in the flip-flops. All right, so we discuss here timing, very important timing, and we assume only in a very small proportion the propagation delay of these gates. For instance, in this case, we took into consideration the propagation delay of the inverter here for the clock. You see this clock is slightly shifted in time, and then also the outputs of the flip-flops, etc. So next we want to see more in detail the effect of this propagation time in this particular flip-flop. Very important. So the change of the clock we have seen is crucial. Okay, determines the whether the input reads correctly through the output, and we always refer to that critical point in time. Okay, so however, we need to guarantee that the values of the input to be correctly read into the flip-flop needs to be not at the exactly same instant of time in which the input is going to be read, but we need to guarantee that before the change in the clock, the input has been stable for a certain amount of time. And that's what we call the setup time. Okay, so it's not exactly at the same point with the clock is going to change, but that slightly before. And we need to keep that at least during the setup time, okay, before the clock changes. And also after the clock changes, we need to keep the input also stable for a certain amount of time. So not only before, but also after the rising edge or the falling edge of the clock, which is the instant that determines the change. In other words, let's see how we depict that. See that this is the input for a D flip-flop, the H trigger flip-flop, and this is our clock. In this case, the graphics basically says that, okay, let's take care of the clock when the clock is going up. Now, see what happens. We also have another propagation time that's part of the, I would say, a part of the electronics or the physics of the circuits, as well as this setup and hold time. We need to include that into our time. Okay, so if we consider this is going to be our input, we need to have the input stable right before the transition of the clock, the one that we're interested in, okay, and after the transition of the clock. So that's what it is depicted, right? So the clock comes. See that the output is not immediately changed, but it certainly takes some time in which we know that this is the propagation time. Okay? So similarly here, we're changing, the input is going to be read as a 0. The input here was read as a 1, therefore the output is a 1 on a D flip-flop. And here is a 0, and then we also see that the change comes after just the propagation time from the output of the flip-flop. Good. So all these times are crucial and very important that we keep in mind and control in our design. So these three times, the setup time, the hold time, and the propagation time, will in certain ways determine how fast we can use the flip-flop. All right? And this is a circuit that we use for that purpose. This is a circuit that in certain ways, it's very simple to understand. We have a D flip-flop. We already know how to follow the D flip-flop. And what we do is just the output is feedback into the input, but inverted. What's going to happen? Well, let's for the moment ignore the clock. But for any change that occurs here, then whenever the clock is active or demands or enables the change, then we see that because the input is always the opposite of the output, we want to start toggling back and forth from 0 to 1, 1 to 0, 0 to 1, 1 to 0, and so on and so forth, as whenever this clock changes. Okay, so in other words, imagine that this is the clock. The clock is also, we're considering the rising edge type of clock or flip-flop. Of course, this is given because of this triangle here, remember? And, okay, whenever the clock changes, the first immediate change will be felt in the output. So the output will change based on what? Based on what is reading here in the input. So let's assume that the input in this case is being 0 for a while. So when we see that the input is going to be 0, then what's going to happen? The clock comes and Q, of course, is supposed to be high because it's opposite, and it's been a long time without a change, so Q is going to be high, right? And the clock will come, right? And the input in this case is the output will change. Okay, the output will change following the input. The input at this point is going to be read as a 0, right? Right here we have a 0, therefore it demands a 1. It demands a 1, and this is a propagation time from the flip-flop. From the time the clock changes from low to high, senses a 0 here, and then will proceed to change from 1 to 0 back here at this moment. This is the propagation time or time internal into from the flip-flop, right? Of course, after this output changes, what's going to happen? Well, the change is immediate, transmitted to here. We see there's a path that falls. Let's assume there's no time delay in the wire. However, there's some time delay in the inverter. So the inverter will sense that now this is not longer a 0, right? But in this case, it's no longer a 1, but a 0. Then convert after a certain propagation time from 0 to 1. Okay, and that's what is going on here. After very small propagation time from the inverter. So we have here the time of the clock, time of the change, propagation time of the flip-flop, and then the propagation time of this inverter. Now, what is exactly is going to be the next change? The next change is going to be right here, okay, from rising edge to rising edge of the clock, as we showed in the last example. Now, here's the thing. If we put everything together, what do we need to guarantee? We need to guarantee that all this time between changes are so, or they accomplish the following. I need to be sure that my propagation time of the flip-flop plus the propagation time of the inverter plus the time required to keep the input D stable before the change or before the clock, which is the setup time, all is shorter than the whole clock cycle. You see, from one change to the next, I need to force these 3 times to be there. Okay? So, in other words, let's assume that we have a, that's the clock period, If you know that there's a relationship between the period and the frequency, we could then find with this formula, with this expression, we could find the maximum frequency that we can use to handle this particular flip-flop. Now, see that, or this particular circuit, we're including here the inverter in this case. Now, suppose if my period is certainly, for instance, 10 milliseconds, I need to check whether these times are correct and are at least, at most 10 milliseconds. Okay? If I require more time, that means that I probably will not have the corresponding setup time. I will not have ready my signal to be clocked and then transferred because it's not going to be stable. All right, so this is the example of the book in which the propagation time of the flip-flop is 5 nanoseconds. The propagation time of the inverter is 2 nanoseconds. And the setup time of the flip-flop is 20 nanoseconds. If we add these three values together, then our period, the minimum period required for this particular circuit will be 10 nanoseconds. And then we want to see some examples in which, or with this case, in which we're using different clock times. Okay, the first one is one in which clearly we have 5 nanoseconds. Okay, in this case, it's our the propagation time, in which we, after the clock changes from 0 to 1, you see that's all the time it takes the flip-flop to change from 1 to 0. And then we also have 2 nanoseconds on here, on the inverter, that will add 7 nanoseconds. And then we have our 3 nanoseconds of the setup time, and you see that is not satisfied. So we clearly have this time is less than 10 nanoseconds. Okay, you see these two times are overlapping. This case is clearly it's satisfying because we have our 5 nanoseconds. You see, after the clock changes from 0 to low, the Q changes from 1 to 0. That's what happens. Then 2 nanoseconds more, our input here will change because of the effect of the propagation time in the inverter. And then we also have 5 nanoseconds and then 3 nanoseconds more for the setup. So we have plenty of time. So if you see how long it took for this cycle in the clock, is clearly 5 nanoseconds plus 2 nanoseconds plus 5 nanoseconds is 12, plus 3 nanoseconds is 15. Clearly, we can make this clock faster and still comply with these values that we are required here. How? Well, we can reduce, what would be the amount? I mean, to make this at least 10 nanoseconds, we can reduce this pretty much to 0, right? To this time here, we can just shift here and then have our 3 nanoseconds, 5 nanoseconds, and 2 nanoseconds. Okay, so remember, if it's not squeezing this only because it's probably the clock is symmetrical, so we can manage to, as long as we have the whole period of 10 nanoseconds, we're fine. Okay, and at this point we actually reduce that to the maximum clock period. Okay, I'm sorry, the minimum clock period, that would be the maximum frequency. Okay, careful with that. Okay, good. So this is a very important thing. We want to look at some examples later on how to deal with the timing. All right, I'm gonna stop that here, and we'll continue with more in flip-flops. Don't go.